First thing I'm going to do is I'm going to share my desktop and bring up Designer. With respect to Designer 5, we've made some changes in there. And the first change that I think is very important from an analysis perspective is the usage of Network Data Explorer for looking at touchstone information or network parameters. Previously, you had to have a Nexum circuit added in to here. So in other words, I would have to go to Project, Insert Nexum Circuit Design to be able to use Network Data Explorer. We have changed that now. You'll see I have no circuits, nothing underneath my project. I just have an open project. I can now use Network Data Explorer this way. So all I require now is essentially a pre-post license to operate Network Data Explorer. So I'm going to open up Network Data Explorer, and you'll see here Network Data Explorer has the ability to browse for touchstone parameters and actually NMF files as well, if you're familiar with NMF files. What I'm going to do is I'm going to go ahead and multi-select. I use the Shift key, but you can also use the Control key as well to multi-select. I'm going to multi-select 3 cases here. These happen to be differential pairs, a 1-inch line, a 12-inch line, and a 20-inch line. Okay, I have a few more joins. Now I'm going to say I can plot this information over all frequencies to understand what is over all frequencies. What does my 3 plots look like together? Well, in this case, it's not all of them. This is just the 12-inch, which is lowered into memory at this current point. But I can do a comparison if I want. But more importantly, I can quickly and easily plot the touchstone parameters. So, for instance, in this case, I'm looking at S11. I'm looking at the insertion loss now as well. But the thing that's nice about this is that I can go through now and define differential pairs. So I come down to here and I can go into define differential pairs. I create a new pair. In my case, port 1 is positive, and then port 3 is the negative case. So I have to define that. I'm going to refer it to 100 ohms for my differential mixed mode, and then my common mixed mode would be 25 ohms. I'm going to hit a new pair, which would be ports 2 and 4, and I'm going to hit OK. Now I have, as you see over here, it updates differential pairs defined. So I can look at differential return loss, differential insertion loss, common mode. Let me find the common mode one. Well, notice how there's a common mode on port 3 with return loss. Notice how I have to kind of go through this. And if this ends up being a very large matrix, for instance, S18P, that's an 18 by 18, that can be kind of unyieldy. So I can also come into here, and we added the capability to do cell filtering. And I really like this capability because what it allows me to do is say I want to look at just return losses. I hit return loss here, and I get to control the ordering here. This is based off of, what does it look like for return loss? If I want to look at I+1 return loss, I can look at SDD11. If I wanted to see the opposite end, I'd say the reverse end, and I got SDD22 there, and common mode. What about insertion loss? I can do the same thing with insertion loss. You see I have SDD12 here. I have the common mode insertion loss. I can also undo the reverse order and look at it in the other direction. So I have the capability of making my analysis of different S parameters very easy. Now, so the cell filter is very useful, especially for large S parameters. Now, what if I want to go through and do my comparisons? As I said, I'm going to go to data sources. You see here, the 12-inch is the active one. I'm going to tell it to display display plots for all traces and data sources. I'm going to hit OK. Now you can see here on my same display, I can see the different characteristics for all 3 of these. Return loss as well, if I want to look at return loss. Now, I said we can also do comparisons. I can also come into here to do a comparison between the S parameter files. So now you see I'm doing a comparison, which is basically a one-to-one comparison between the 12-inch line and the 1-inch line for SDD11. And this is the differences between SDD11 here. I'm going to move on. I just wanted to show you this capability and show you that it's very good understanding S parameters and analyzing S parameters, adding in the mixed mode solutions, which were previously not there in version 4.1. Any questions from anybody before I move on?
This is Jason. I see that return loss is over 0 dB. Why is it happening?
That was because I did remember I said I was going to do a comparison between two files. So I'm going to browse. Let me bring in all three files again, okay? I bring in all three files. Let me define my differential pairs. I didn't save what I had just done, so I define my differential pairs. I'm going to add a new pair. Hit OK. And I'm going to plot it. Now, if I look at dB, let me go to dB. If I look at, and let me go to data sources. I'm going to turn this off so we don't have any confusion here. If you look here, Jason, you'll see that, notice my actual insertion loss, my STD11 return loss is well below 0 dB.
Sure.
Notice it's minus 5 dB. What I'm going to do is I'm going to compare a file which has the 12-inch. I'm going to compare it to the 1-inch. So this is doing a direct comparison between these. So now I'm not looking at STD11 of an S parameter file. I'm looking at what are the differences between the files.
Okay.
Does that answer your question?
Right. You did.
Great. All right. Any other questions out there before I move on?
Yes, so about the passivity, this can be helpful. Is it showing something or still like the previous one?
Yes, you can actually check for passivity in this as well. So that was actually an improvement. I got to find it now.
Okay, that's another.
We have Eldon on as well. Eldon, do you remember exactly where the checking for passivity is? It's under, I think it's under matrix statistics. Yes.
Yeah. Yeah.
This also will allow people to quickly and easily check for passivity violations. What we did in the first release of this was a simple passivity checker, just looking to see if you're greater than 0 dB. We've now implemented the same algorithm that Nexum uses, which is a more advanced algorithm for looking at passivity violations. So we now can quickly and easily look at passivity violations for our solutions. Let me come into and select another file. Now this is looking at S4P. I want to look at S1P, and I have no. I don't have any passivity violations. I think it's best probably to look at magnitude. Everything's below 1. If I look at S20P, again, everything's below 1. So I have no passivity. Everything's below 1. I have no passivity violations here. Any questions on that?
Steve, is there a way to actually give you a table format of anything that actually exceeds 1? Because on some graphs, you might have a 0.999 versus a 1.01, and it's really hard to tell graphically. But if you have it in a table, especially just looking at violations,
So if I click on table as opposed to plot, I was looking at the plot. If I click on table, I now get a table of my passivity.
But there's no way to filter that for only violations, right?
Not at this point in time, no. Daniel?
Yeah.
Write that down, and we're looking at enhancements for Release 6.
Okay.
And we're going to do some more enhancements to Network Data Explorer with Release 6, so please write that down and send it to me. Any other questions?
Does it also have capability of doing some synthesis into rational function polynomials?
No, Network Data Explorer does not do circuit synthesis. However, Designer does do full wave, what we call full wave spice solutions. So traditional Designer can create a rational fitting polynomial for a spice subcircuit.
Does it also have a graphical interface? So once it is synthesized, we can co-plot it with original version so that we can make sure that it's well aligned, things like that. The original I think it's full Maxwell Spice server. It is just texture driven, so it does not have graphics interface. So does it now have that one?
So the answer to your question is not easily. Not as easy as Network Data Explorer probably is the better answer. You can create the subcircuit, put the subcircuit into the schematic and run a linear network analysis, and then do comparisons that way.
Oh, okay, I see. All right.
But you can't do it just by click of a button like you can here.
All right.
It requires you to do an analysis. Eldon, do you have anything else to share with that?
No, unfortunately, that's the way it is at this point.
Okay.
But Daniel, you might write that one. I'll use Daniel as my log taker. Can you write that down as well, Daniel?
Sure.
Thanks. So I'm going to move on. Any last second questions on this, though, before I move on? Okay, great. The next thing that I want to go into are some new options that we have. Specifically, I'm going to insert an Nexum circuit design, and I'm not going to use any layout technologies. And let me go ahead and save this as a training event. I'm going to save it right here. Okay. The next thing I want to show is another new quick and simple functionality, which is can be very useful. Previously, if we wanted to import library files or include files, we had to do them one at a time. We've added a new tab here called Add Multiple Library Include References. So what this does is, let's look at the browse netlist. Currently, if I browse this netlist, you'll notice that my netlist basically doesn't have anything in here. If I come to here and add multiple include files, I can I'll point to some W elements, for example, and I can use the Shift key now and highlight all of them at the same time, open it up, and you'll see that all of those are included. Now, if I refresh this, I'm going to just browse it again to refresh it. You'll notice that all of those files have been included. So it's a much easier way as opposed to defining those individually each time as we used to do through this menu box. So it's just a very simple. I can also delete these, so I'm going to go ahead and delete all of them since I don't want to use them. But that's the ease of use item that can be very, very handy. Any questions on that before I move forward? Okay, I'm also going to show another, what I'll call very good improvement to the UI. I want to add an import model. So I'm going to go to Project Add Model, just like I used to, and I'm going to point to my file. And I got some S parameters here. I got the same S parameters. I'm going to just import the 1 inch. Notice here, question?
Just a quick question on that library import. Can that library import value be parameterized?
I'm going to show that next.
Okay.
Because you're going to do it a different way, Daniel.
Ooh, all right.
But it's easier even than that. So.
Okay.
The next one is you're going to see we've changed the default. The default used to be import data, but now the default's linked to file. This is because you don't want to be actually importing all this large data into here. It's quicker to do link to file. You'll also notice that we have a checkbox here that says, if I have a valid state space solution for this S parameter data, use state space in my solution. This is because we want to enable state space library management. This is a huge savings in time once you get and create .sss file, which is our format, which is the extension for our state space solutions. This is going to be very important as you do very large batch mode type solutions that you create this one time. Let's say I have VIA, and that VIA, I parameterize it, and I have 3 different touchstone files. Create my state space files, and I can reuse those same state space files as I do my parametric analysis over multiple computers. And so if I'm using convolution, it may take, a minute to 2 minutes for this to run, but with state space, it'll take a matter of seconds. But there's another thing that I want to show you here. We've also added in, if you're using state space models, the traditional enforced passivity, but we have a new button called Passivity by Perturbation Algorithm. Passivity by Perturbation Algorithm is a new algorithm that was created to handle larger port touchstone files. And the reason it does a better job than the traditional enforced passivity is it's the way that they start guessing the it's the way that they start guessing the initial seed value. It's a smarter algorithm for guessing that seed. So the use passivity by perturbation algorithm is very good for large port count S parameter files if you're trying to do a state space model on it. But the real UI thing that's very nice is now when we bring in an S parameter, we used to only let you bring in an S parameter that was 1, 3, 2, 4. And if you wanted to change this, you had to go to the symbol and actually change the symbol itself. Well, now we allow you just to click a button and it'll automatically change it. Port 1 goes to 2 now, 3 goes to 4. As before, it was 1 to 3, 2 to 4. So now we can, by clicking on a button, change the symbol that will get dropped on the schematic. You can do all left, all right, odd, even, 1, 2, 3, 4, as you see here, or you can even do a manual. I can drop this over here, or drop that over there. So that's a nice UI change there. Any questions on that enhancement before I move on?
So I am following your the import data in the tab options. The DC behavior is grayed out. Not sure why it's not accessible.
Oh, because it's not a. That's because in this particular case, that S parameter file doesn't have a DC solution.
Oh, so I think a DC behavior is more like extrapolation to the DC value, right? Yours has. If I look at yours, yeah.
Let me go to it before I comment anymore to make sure I say the right thing. Here. Nope, under options.
Right. DC behavior, it's I can choose some options out of this, and I just open another S8P, and then I don't have the access there. It's grayed out.
If DC behavior is grayed out, then you have the DC information in that S parameter file.
Oh, I see. Okay.
Yes, thank you. I guess that's what I tried to say, but I said it incorrectly. Did that answer your question?
Yes.
Okay, great. And let me state this. It is much better to have a DC point in the solution as opposed to using an extrapolation. We would much prefer you to put in the DC point from the model that you get. Now, sometimes that's not possible, which is why we offer this. But it allows for much easier convergence if that DC point is there, and it would give you a more accurate answer.
I have another question. In
Okay.
the method, there are four methods: convolution with IFFT or piecewise linear transform. Can I look at a bit further on this? What each of this is in computation?
This could be a long conversation. We're putting together, so with version 5, it's not completely done yet, but we're putting together a flowchart with more information on specifically on the different convolution methods, or excuse me, on the different methods for handling S parameters. So let me defer that question to later and take it offline with you, because that's a much more in-depth discussion, okay?
Sure. Yeah, right. Okay, thanks.
All right. So I'm going to cancel out of this. Now, I'm going to start showing some new functionality that wasn't there that'll be very important moving forward. So before I change subjects again, is there any more questions? All right, great. Actually, I wanted to show one last thing too. Let me run an LN. I'm going to change the name of this. I'm going to run a linear network analysis. Okay, I'm going to import project, add model, just as I did. Import model. I'm going to point to the file. I'll do a 12-inch. Hit open. I'm going to go to symbol. My through path is 1 to 2 and 3 to 4, so I'm going to hit OK. And now I have a model created that I just called model. But what I want to show you is under Nexum circuit, I need to drop this on the schematic first. There's new options here. Implied reference to ground, which is generally what I use. The traditional show common reference. This one we really will not use often, but this one might be one that's important to use. This will show you the reference pin for every pin. For instance, I'm going to drop it on there, and if I drop that on there, you'll see now I got port 1 reference, port 2 reference, port 3 reference, port 4 reference. But remember, all these references are tied to the 0 node eventually, so I'm going to delete that and redrop this onto here and just use the traditional port 1 to 2, 3 to 4. I'm going to go ahead and get my ports. 1, 2, 3, 4. I'm going to come up to here and go to Next Circuit, and notice there's a new button down here called Differential Pairs. I'm going to click on Differential Pairs, and now I'm going to define the new pair, similar like I did in Network Data Explorer, but I'm going to define it inside of Designer proper and hit OK. Now I'm going to come into here and run a linear network analysis, so set up LNA. And let's go from DC. I think these stop at 15 gigahertz. Let's do 10. Let's do a 10 megahertz step. Hit add. Okay. Okay. I'm going to right click and analyze this. Analyze. Goes through and analyzes. Now, I'm going to plot my report. I'm going to create standard report, rectangular plot. Notice that I now have differential, or I shouldn't even call it differential. I have mixed mode S parameters in my report editor. This was not there before. Previously, you had to go to output variables and define this yourself. Now, by defining the differential pairs, you can come into here and look at, for instance, this case is the insertion and return loss. Something happened. Okay. I'm going to do a new report, add my differential insertion loss. I'm going to add in my differential return loss for SDD11. But notice I can also select terminals. So if I select terminals, now I have my traditional 11, 12 that are single-ended terminals. So I can now define differential pairs in the report editor. If I click on return loss, you see down here under return loss, well, it's not filtering it now. If under terminals, I can look at return loss as well. But the real power here, though, is that we have S parameters that we can do with mixed mode in the traditional report editor. Any questions on that?
What is the RTL? Is it return?
That's return. So right, this is a return. This shows the return loss.
RTL, right.
And it's showing it for the terminal parameters 11, 22, 33, and 44.
Okay. What is the difference between DB and DB20 normalized?
Eldon, do you want to answer that one?
What was that question again?
So there is a function DB, and there's also function DB20 normalized. Is there any difference between these two?
There shouldn't be.
Shouldn't be.
It's just DB10 and DB20 depends. They're generic modifiers that might deal with either power or think of it as like the S parameters. So if you have power, you don't want to do DB10.
Right.
Right.
But his question is, why have DB and DB20?
I don't know. For this case, I don't think it matters.
Right.
Right.
I think it's the same thing.
I have another question. Can you show me once again how to instantiate the symbol of the schematic?
It's just double-click on LNA, and then I grab the left mouse click and drop.
Oh, okay. Thanks.
Okay. All right. I'm going to save this. Now I'm going to move into some more advanced topics. I'm going to window close all. And I'm going to add in what I'm going to call Project Insert Nexum Circuit Design. I won't use any layout. And I'm going to call this this is going to be traditional IVIS_transient run. Okay. However, with this traditional IVIS transient, I'm going to do things a little bit differently. The first thing that I'm going to do is I'm going to show you how to import arrays so I can sweep such things as tabular W elements, sweep touchstone parameters, sweep the typical fast, low behavior of IVIS files, sweep what I'll call string variables, I think is a good way of saying it. I'm going to show you what happens here as well. So the first thing to do is you'll notice in here that there's two ways of doing it. One I'll call, we'll go look at tools, import array from table. There it is. The other way is a methodology that we can set this up manually. What I want to show you, though, is first I'm going to come into here, and I'm going to go to what I'm going to call DOE tables. And this is a CSV file. You may get this information from a third-party vendor. We actually offer a solution ourselves that ANSYS offers called Design Explorer for coming up with these response surface curves. I'm not going to go into using the response surface methodology called Design Explorer during this training. That'll come at a later training. But what I want to show you here is if I have a numeric table that gives me my response surface solutions that I want to simulate, you'll notice here I have 1, -1, zeros, 0.5, -0.5. I'll call that my element mapping. And I'm going to map that to the parameters that I want to sweep in my solution. So you'll notice I got text bit patterns. I have S parameters here. I have IBIS speed parameters. I have a transmit resistance variable. I have different W element models. I have different lengths for my W elements. I have different output resistances. And I'm going to also sweep my IBIS AMI models later on. I'll show you that as well. So I want, everywhere that there's a 1 for bits, I want that to be referred to the K28.5 pattern. Everywhere that there's S4P with a 1, I want that to refer to 20-inch. If I have a table like this, I can set this up and go to, we have a little utility called DOE Import Expert. And all this little utility does is take this Excel file here and converts it into the format that designer needs. You can also create the format that designer needs automatically, but it might be rather painful. This will do it for you automatically. So I'm going to point to this. Actually, I have to close this out. Let me point to this file. I'm going to hit open. And I'm going to tell it to write the variation matrix. And I'm going to call this sweep_Steve. Now it wrote that file out. And if I look in here, I have sweep_Steve. I'm going to drop that back into Excel. And what you're going to see here, this is the format that designer needs. So the format that designer actually needs is the bit index here, followed by the pointers to what it's going to point to. You can create this manually by this way, but it could take you a long time to create a file like this. Or if you start with the numeric response surfaces that you want to sweep, we have the utility to automatically create this for you. A couple things with this that I think are important. Notice that when I point to a file, I'm using $project_dir. The reason I'm doing this is this maintains a relative path. A relative path is important if you want to share this with your colleagues. If I type in C:// Steve // I can hard code the path name, but if I pass this file along to one of my colleagues, it'll be hard coded to my computer setup. I can't pass it easily. So by using project_dir, I can use relative paths here as well. Notice that if I'm creating this file, that I have quotation marks around the project directory locations, but everything else I don't need quotation marks. Any questions on this? I'm going to come back to why we're going to use this, but that's the first step in this.
Did you have a parameter that controls the number of bits you're going to simulate?
I do. So if you look in here, let me go back up. You'll see that I'm pointing to different files. So here I have a PRBF7, which is just a text pattern. I'll open it up. Give it a second here. So here's a PRBF7 pattern. I also have a K28.5 pattern. I have in this one a 9 and 11 pattern. So I'm pointing to, in this case, different PRBS patterns. You'll notice here I have IBIS AMI. The ones that are important that I'm pointing to is MyParams1, MyParams2, and MyParams. I'm going to come back to these three and explain those later today. I'm pointing to different S parameter files, so you'll see that I'm pointing to 1-inch, 12-inch, and 20-inch in that file. And I'm also pointing to different W element models. So in this case, I'll do 2 lines. I'm going to point to, in this case, I pointed to 47, the microstrip 47, microstrip 57, microstrip 64, the strip line 41, and the strip line 51. And I know that because I created the files, but if you look here, you'll see that I'm these are the models that I'm using. Does that help explain this?
Yeah. Well, what if you just want to do like 100,000 bits of random data? So do you want to create a file to do that, or do you just want us to do that for you? We have a methodology of doing that directly inside of Designer. I'll show you that in a minute, okay? Okay. So now the next step that I'm going to do, so I'm going to set up a sweeping solution is what I'm going after. I'm going to go to import array from table. So I'm going to go and point towards this sweep Steve file that I just created. Notice when I open that up, it says, hey, look, I found these array index variable names, and I want to create these array variable names. So I got, in my parameters, I had AMI params, and it wants to create the array. I have a speed, it wants to create the array. The models for W elements, W2 line, and the array. The bits, and then the bits array, the S4P, and the S4P array. I'm going to tell it to create this. When I click Finish, notice if I click here, it's showing me my design properties, and you'll notice that it created all of these for me. So if I right-click, well, there's different ways of doing this. The old way that we used to do this is right-click and go to Design Properties. And if I go to my local variables, because all of these are locally defined, we cannot, this is an important point, we do not create these sweepable arrays at the project level. We create them at the circuit level. That's an important point there. What that means is, notice at the project level up here, which has a couple of different circuits underneath of it, I don't have anything to sweep. At the local circuit level, I have this to sweep. I can also double-click there, and that'll open this up. And what you're going to see here is that I'm pointing to exactly what I talked about. So let's look at, to help understand this, I'm going to point to S4P array, okay, and I'm going to edit it. And notice here that for S4P, my file called out the 1-inch, and it called out a 20-inch. And notice how I've got this inside with is required, if so, is a string array. Notice how I have these in string arrays. So all I did here is I assigned 1-inch an index of 0, and I assigned 20-inch an index of 1, and I'll come back to why that is. And then over here for my S4P, if I edit this, you'll see that S4P has a value of 0. Well, I can take S4P, which is going to be my index index parameter, and I can sweep S4P from 0 to 1 in this case. If I look at bits, let's look at bits, because there's more in there. Well, I thought there was more in there. You'll see I have K28.5. Let me find something that has more in there. Edit. Okay, now if I look at my W elements, you'll see I have 4 different models in here: microstrip, stripline, and stripline. Now, I can sweep my index array from 0 to 4, and I'll show you how to do that later. So what I did by importing that is I added in variables. So that was step 1. And I have a PowerPoint to show you how to do this to help you out, because it would take a little time to get used to, but that is step 1. Now what I want to do is show you a new methodology that I have to do. If I want to sweep W elements and I want to sweep S parameters, I have to do this. But I can do this anytime I want. But if I want to do sweeps, I have to do this. We have a new thing down here called import SMP and import W components. So remember, there's other ways of doing this. You can go to project, add model, add import. That was what I showed you. And previously, what we would do is we would right-click on here and add in the data file for the W element and drop the W element down. We've made this a little bit easier, because now I can come into import SMP or W. So I want to import a W element. It has 2 lines. Let me show you what this does first. I think this is important. So let me go to browse this netlist. Notice this netlist, I've got my .param statements, but I have no include files in here. I'm not including any .inc files. I have no include statements in my netlist. So now I'm going to come into here, go to Tools, Import W Components. It's a 2-line element, differential pair, add files, and I'm going to come to my W element 2-line, and I'm going to select. I can select them all. I can select some of them. The ones I'm using, I think, are. I don't remember exactly which ones I'm using. I think it's 47.
Let me make sure I know which ones I'm using before I go off and do that. So if I look at W2 line, and I go to edit this, you see I'm doing microstrip 47, microstrip 64, strip line 41, and strip line 51. So I can import them all. It doesn't really matter. Why don't I just go ahead and do that? I just import them all. Add files, go to my W elements, my 2 lines, and I'm just going to highlight them all. And I'm going to hit, I don't want Steve SP in there. I don't need that. I'll just highlight some of them. And I'm going to hit open. Now you'll see that I'm going to bring these in. Now I'm going to update. Now I'm going to come back and update after this loads. I'm going to update my net list. And I want to show you what this does for me. Because remember previously we had to do W elements. We had to right-click on data and add them individually. By doing this new method, you don't have to do that anymore. Notice it created a new custom component called transmission line W02 custom. That's important. So I go back to my schematic here, and I go get my component, transmission line W2 custom, and drop it on my schematic. And now I'm going to browse my net list again. Notice now that one W element automatically did the .INCs for those different transmission lines. Any questions on that? It's an easier way of importing W elements to use them nowadays.
So the import is project level. I thought that you import the W element in the IDIS transient, but then it also can be seen in the LNA circuit. This is not the LNA circuit. This is the IDIS transient. If I look at the browse net list here, I don't have those .includes. But then under the LNA, there are some models that you don't.
This is not, so definitions is common for those.
I see.
Okay?
Got it. Thanks.
Okay. So I've included the .inc files here now. I've included all of these.
A quick question for you.
Yeah.
Net list format that you're showing here, is it used both by Nexum and by QuickEye, or just Nexum?
Well, so Nexum is the engine. QuickEye is an analysis that Nexum performs. So notice if I come to analyses and I have all of these analyses are Nexum analyses. And remember that Nexum uses a SPICE net list to actually give a solution. Designer is just the GUI that sits on top of the analyses.
Yeah.
So if I do QuickEye, I actually still create a net list. It's not going to be compatible with other people's circuit simulators because QuickEye is specific to Designer, but it still is going to net list it out.
But you're saying that QuickEye uses the same solution engine as like a simulation that would involve transistors?
What I'm saying is that in Nexum itself, so Nexum is the engine. Nexum is a fundamental type of differential equation solver. Now, the way that we use Nexum is different. You can use Nexum for transient analysis. You can use Nexum for QuickEye analysis. You can use Nexum for verify. We can use Nexum for envelope analysis, transient noise analysis, or TV noise analysis. Now we can do AMI analyses. So Nexum is a differential equation engine wrapper that has a bunch of different analyses that use the underlying mathematical constructs that are part of Nexum. Does that help answer your question?
Well, my understanding, and maybe it's not correct, I thought Nexum was still a matrix solver like SPICE. And it just was more efficient with its use of device models and with frequency domain models for interconnect. Did I not understand that correctly?
Well, I think what you said probably is a very subtle point. Okay, what you said is not completely true. Nexum solves differential equations. It's just how do you employ the solution of those differential equations. And one of those ways of solving those differential equations, is using a transient analysis type. And that's the specific type you were talking about. Now, QuickEye does a traditional transient solution for the step responses, but after it does the step responses, then it goes off and does a convolution technique to do superpositioning on a linear channel based off the bits and based off of the step responses.
Which is an entirely different solver.
It's an entirely different way of using the information that's there, is correct.
But hold on, Steve. It is still a matrix differential equation solver, just like any circuit tool. But the specifics are how do you model a given component. And so I think your issues have nothing to do with the solver, but how do you represent the model. And so Steve's been really trying to tell you about how we represent the model in this case.
Right. I don't think. I guess the question I would ask is, does it really matter? And from a user standpoint, Nexum is the engine that runs all the analyses. The mathematical constructs are only seen by the people that wrote the original C++ code that Nexum uses. The different types of analyses that we have here, in some ways, use different parts of the code and different parts of the mathematical constructs.
Okay.
It's just how the analyses are applied to the Nexum engine.
I don't want to bog your meeting down, so maybe we can take it offline. But it does matter to me how the solver works and how the solver uses my model, because that's going to have a direct result. How do I want to say this? Directly affects the accuracy of my solution.
Right, but your question isn't how do we solve it. Your question, I think, if I understand, your real question is, if I use QuickEye, I'm doing a convolution with bit patterns, and that makes the assumption that I have a linear time invariant circuit. If I'm simulating transistors, they're not linear time invariant, hence I break the assumption for the convolution piece of the QuickEye analysis. So that may not be the appropriate way to use it.
Yeah, I would think that you couldn't even bring a transistor level model into a QuickEye analysis.
But you can. And depending on how the transistor level model is created, will depend on whether you can get good answers or not. But that's a whole other discussion on LTI and what happens. So that we should table to offline discussion.
Yeah.
But I can go into details of when to do that and when not to do that. Okay. All right. Sorry about that, everybody. So I've created a W element. Now I'm going to come back and I'm going to do tools, import SMP and W components. Again, I'm going to select W or S elements. I'm sorry. I'm going to say I have a 4-port device. But I'm also going to go to options. Notice here I don't have a nice picture, but I can go odd even, which would be 1 and 3 on the left-hand side and 2 and 4 on the right. Or I can do I, which would be 1 and 2 on the left-hand side and 3 and 4 on the right-hand side. I know mine are odd and even. I have a couple options for the references. I'm just going to assume it's implied to ground. Do I want to create a sweepable array for touchstones? If I'm doing this in a different technique, I may want to do that, but right now I don't need to because I imported that array already. And I'm going to do, for this perspective, I'm going to do convolution, and I'm going to hit OK. And I'm going to go to add my files. I'm going to go point to my S parameters. I'm going to highlight them, bring them in, hit OK. Notice I created a custom component called SLMN custom. I'm going to hit OK. I'm going to grab this one, and I'm going to drop it onto my schematic. Now I'm going to connect it up. I'm also going to come into here, and I'm going to import an IBIS component. So I have an IBIS component that I want to use. So I'm going to point to IBIS. I got this off the web. I think it's free for everybody to get. I just went to Altera's website and grabbed it. I'm going to open this up. And what I'm going to do here is I'm going to do an IBIS solution on PCI-X. It's a simple solution, but it's easy for everybody to, I think, understand what's going on, and it'll simulate fairly quickly. So, but you could apply this to DDR memory solutions as well if you're using, or clock signals, or whatever it is you're doing. I don't want to create a model for every single one, but I do want to use the package model that comes with it, just the lumped circle equivalent. So I'm looking for PCI-X. Got to find it here, sorry. Here's PCI. Okay, so PCI-X, I want to do this. I'm going to do the input buffer, so that's my receiver model, and then I'll do the I/O model, the input-output buffer model, and I use this as my driver. And I'll do S3, which happens to correspond, if you read all the documentation, to the fastest slew rate. So I'm going to bring in just these two models. I'm going to hit OK. It's going to go through. Now, I must tell you that this .IDS file that has all these models in it is a 65 megabyte text file, so it took a little while to parse all of that. But I come over here and you'll see now I have a PCI-X input-output and a PCI-X input model. I'm going to grab my input model, I'm going to drop it over here. I'm going to grab my driver model, I'm going to drop it over here. And I'm going to come to components and I'm going to grab a couple resistors. I'm only adding these into the circuit because I want to parameterize them later. Other than that, they have no meaning. I call this one R out. I'm going to copy it, Control-Z, paste it. I'm going to call this one RTX. Hit OK. Notice everything's a local variable. Now I'm going to come up to here and I'm going to connect up my circuit. Oops, excuse me. I'm going to use the ideal power sources. I'm going to come to here, enable it. I'm going to put this up here a little farther out of the way. Now, you'll notice that I've more or less created my circuit now, but I haven't created all the pieces and components. I need to grab one other thing, BPRBS digital. I'm going to create a input bit source to my IBIS driver. I'm going to ground it. And hit Control-D. Okay, now I've created my channel. I'm going to save it. Now, the reason I haven't created my entire is because I want to do some cutting and pasting. But remember, I told you that we can sweep bit patterns and so forth. So the first thing I want to do is I'm going to hit bit file. Let me go back so I can show you what I'm going to do a little bit clearer. Minimize this. I click on IBIS transient here, okay? Notice that my array is called bits array and my index variable is bits. So I'm going to come up to here and I want to sweep the bit pattern. So I'm going to hit bit file. Notice here, if I read this, it tells me to add a plus signal if I want to do a sweepable parameter. So I type a plus and then I say bits underscore array. So that's the array that is a parameter statement. I do a bracket and then I type bits and then end the bracket. So this is bits array at location right now. Bits is defined as a parameter of 0. So this is bits array at 0. Or if I increment that, it could be bits array at 0, at 1, at 2, at 3, and so forth. So I hit OK. Let me go to the netlist to show you what that did. Browse netlist. If I come up into here, notice I said this was a parameter statement. Bits was currently defined at 0. And bits array is all of these text file pointers, remember, that I created. So if I go to bits 0, that points to this first one. If I go to bits 1, it points to that one. If I increment it, okay? If I look at my my BPRBS source, if I look for my voltage source, I have to find it. I got voltage 18, net 9, 0. Notice here, what bit file is it pointing to? It's pointing to an array that has an index of bits. And I can increment bits. Any questions on what's going on when I did that? Okay. All right, so I created that. So if I look here, I got my bits array. This is IBIS, so 0 to 1 is fine. My rise time, I don't know, we'll do 100 megahertz signal, so I'll do 1 nanosecond. For fall time, we'll do 1 nanosecond. We'll do 1 divided by 186. Oops, I forgot. For my UI, and if I look what UI that corresponds to, it's 100 nanoseconds. If I did my math right, or 10 nanoseconds, if I do my math right. Okay, so I've got my source selected. Now I point to my IBIS driver model. I want to control, I'm going to leave power on. Notice down here I've got my pin name. I can select package or pin or no parasitic. This is just a lumped equivalent model here. I have all my IBIS options shown here in the GUI. I'm going to come into here, though. Notice I've got typical, mid, max, fast, low. I want to sweep this. So I'm going to come over here, and I'm going to add a plus sign. Remember the plus sign, because I'm pointing to a text variable in this case, and I'm going to type in, and if I look at what it is that I got to type in, you'll see that it's called IBIS speed array, and then the index is going to be IBIS speed. IBIS is a reserved word, so I can't just use IBIS, so if I type in plus, IBIS underscore speed underscore array, open bracket, IBIS underscore speed, close bracket, and hit enter. Now I'm pointing to that text array. I hit Control-C to copy that. I'm going to come over here, and I'm going to do very similarly. I'm going to come over here and type in and paste the same thing. So now I've created that one. The reason I had not already done this is I want to Control-C that, Control-V it, and now add it down here. And then I'm going to copy this, Control-C, Control-V, and add it there. So now I've copied the same exact thing. Now, for my W element, I'm going to add in a length parameter, length. Oops, escape. I got to type it right, length. I'm going to put 10 inches in. Notice there's something else that changed. The default now for W elements is table models, not RLGC models. It's table models. Okay, I want to enter in the model name. I'm not going to point to the file because that's what the .inc did. It pointed to the file. What I need here is the model names. In this case, it's going to be an array. If I look at my array, it's W2 line array, and then the index is W2 line. So I'm going to come to here. I'm going to point to W underscore 2 underscore line underscore array, bracket, W underscore 2 underscore line, close bracket, enter. And that was all I had to do for that. For my S parameters, if I come into here, I'm currently pointing to the 1-inch S4P, but notice here I get the same dialog box, add a plus sign if I want to sweep it. So I'm going to say plus, and let me show you what the name is again. The name for this one happens to be S4P array with the index of S4P. So I come into here, I'm going to add in a plus sign, S4P underscore array, open bracket, S4P for my index, close bracket, okay. Now I have created, I'm going to save this, I've created a netlist, browse netlist, that I can sweep. So, for instance, my W element, W6, the table model is pointing to an array and an array index. If I look at my IBIS files, the speed is pointing to an array and an array index. If I point to the bit pattern, I think I showed you this one earlier, where's the voltage source V, I'm pointing to bits, array, and bits. So
did you just do the same thing that you did in the spreadsheet a few minutes ago?
Not exactly. What the spreadsheet is are different instances that I want to sweep. Remember, let me show you. Let me go back up. Remember, I started this out saying I had a DOE table. Notice here, these are all different instances. Each line here is a sweep with different values for different parameters here, right?
Yep.
What I did here inside of Designer, all I did inside of Designer is I set it up so that I can sweep those values or those files. I'm setting it up so I can sweep it. It'll make more sense in one more step, okay? Let me add in a transient analysis, add solution setup, transient analysis. Let's go to 300 nanoseconds. Hit OK. Let me make sure I didn't make any mistakes. The first thing I'm going to do is just run a quick transient. And if I made a mistake, I'll get an error. I'm hoping I didn't make a mistake, but you never know when you're trying to do things live and quick. This warning here, This is a warning that gets passed from the IBIS parser. It's nothing to concern yourself with. I actually asked them to disable it, but they said that sometimes these are important from the IBIS parser. So now it's loading in the entire net list and all of the files that are associated with it. It's going to use convolution, and it goes through and it's going to solve. And it ran completed. So the case that it ran was the nominal case, the case where everything was defined as 0. So let me browse my net list. So the case it runs, because I have all these different arrays with pointers, is everything notice here is defined as a 0 for my index arrays. So it's running the nominal case. Now, this hopefully will answer your question is, I go to add parametric from file. Now I'm going to point to, remember I created the sweep underscore Steve that I used to create my arrays? I'm going to point to it, and I'm going to open it up. And it's the same file without any changes, and you'll notice in here, it shows the arrays that are being swept. And if I look at the table, you'll notice now, these are all the different sweeps. These sweeps here correspond to this table right here. And notice, it's showing here. So the first one I sweep in IBIS speed is a 0, and then a 1, and then a 1, and then a 1, and 1, and then 0, then 2. Our out's changing, 35, 35, 35, 57.5, so forth. RTX is changing, the transmission lines are changing, the bits are changing, the lengths are changing, and the S parameter files are changing. So I've created this huge table to sweep parametrically. Does that help answer your question now? So I can run and sweep all of those cases.
Okay, so you have to make sure that you use the same variable names in the spreadsheet and in the schematic.
Yes, and remember, the way I did that was I did tools import array from table, which pointed to this file right here, correct? Notice it says bits, S4P, IBIS speed, RTX, W2 line, so forth, right? And what did that do? It created all of these names for me already. So these were already created. So when I define them, in my actual circuit schematic, I'm defining what's already shown here.
But you had to type the values in, right?
Here, yes, I have to type this in, yes. I have to tell it, because remember, it needs to know what to point to.
And that value, does that reference something in the spreadsheet?
Yes, notice, I'm pointing to bits array, and it's being indexed by bits. If I come up here, I got bits array, right, which is, let me make this bigger. Bits array is pointing to projector bits K28.5, and then comma, projector bits pattern PRBF11. And bits is the index, so if it's a 0, it points to the K28.5. If I increment this by 1, and then this bits is a 1, then it's pointing to the PRBS11. If I look at my spreadsheet, you'll notice that I have projector bits K28.5 here, which would be corresponding to a bits of 0. And then I go to PRBS11 down here. So this would be projector bits patterns PRBS11, which is be a value of 1. Does that make sense? I'm going to walk. Okay. Well, that's okay. I know it's kind of confusing, and I'm going to set this up another way as well, which will hopefully help you understand it even better. There's two methods of doing it. One is importing this table. Another way is just doing everything manually to set it up. And I'll show you that method as well, okay? So what I wanted to show you before I move on, though, is go to Tools, Options, General Options. Remember I was talking about, and I'm going to Analysis Options, next some Circuit Options. Remember I told you that we now have the capability of doing distributed solve over large clusters? Well, if you have a distributed solve license, you can also run it locally. Notice that I have in 192.168.1.8. This is my IP address for my laptop. Notice I entered it in there twice. I did this because I have 2 cores, and I want to be able to run both cores for my circuit analysis. So I've already entered it in. I'm going to right-click on parametric setup. Actually, I want to do one other thing. I'm going to show you another new component. Remember I talked about statistical eyes? Under probes, there's a new probe called iScope and iScope differential. Well, I'm going to do single-ended, which would be iScope, and I'm going to add it in here, and I'm going to add it in here. What this is going to allow me to do is do statistical eyes. Now, the thing about this iProbe, though, is you got to know some information about it for it to work. So, for instance, for the unit interval, I have to enter that in. I know that the unit interval was 10 nanoseconds. Do I want it to have a delay to it? Sure. How many points do I want to bin? Transient binning is around 500 by 500. However, that can require a lot of data to be saved. If we give up a little bit of accuracy, we can bin less information and it'll be quicker. So there's a trade-off of speed versus accuracy. And this is only this only counts for the resolution of the data saved. And you'll see what I'm talking about a little bit later as I show you an example of what it looks like with and without. I'm going to leave it at the default for right now. Then I'm going to come into here and say the minimum voltage approximately 0, and this is a 3.0 volt, a 3-volt driver. So I'm going to say the maximum is going to be about 3. Then I'm going to come over here and I'm going to do the same thing. So this is going to be 10 nanoseconds. I'm going to leave those as defaults. And this is about 3 volts. And I'm going to hit save. Now, I'm going to run my parametric analysis, and I'm going to run a couple of iterations here. I'm not going to run all of the ones that are listed because it would take too long. I'll run 5 or 6. But notice here, I've got 2 cores, and then I'm going to run 2 simultaneous solutions. If you look, yes, you can see it. If you look right here, this is my CPU usage and so forth. You're going to notice that it's going to jump up to 100% here real shortly, like. So while we're running a couple solutions here, are there any questions?
So you are using IBIS model, which is not necessarily linear, but you're applying iProbe using. Oh, are you using transient right now?
I'm running a transient solution with a new probe called iScope.
Oh, okay. So you don't apply a quick eye or verify yet.
No, I have not gotten that far yet. I'm just doing an iScope solution.
Are you planning to do that? Are you planning to, right?
So I'm going to show you quick eye after this, or I'm going to show IBIS AMI next, then I'm going to show quick eye.
So isn't there any accuracy compromise by adding IBIS model or any transistor level drivers?
Well, of course.
Right.
IBIS models are IV curves, and transistor level models are going to model all the parasitics of the transistor itself. It's up to the end user to decide as to what it is that they want, how they want to model the buffer. Many people in the industry use IBIS as the very first cut. And depending on the speed and the channel that you're worried about, that you want to simulate, IBIS is a good enough solution. It's very quick as well. On the other hand, if you need a very highly accurate answer and you're willing to wait the length of time that's required, in that case you would probably use a transistor level model if you can get a transistor level model.
I'm sorry, my question was how can quick eye or verify deal with the nonlinearity that is introduced by either IBIS model or transistor level drivers?
Oh, I said I wanted to table that discussion because that's a longer discussion. So let's talk about that one after a while, because I don't have time to go into that right now. We have 40 minutes left, and I have quite a bit left to show.
Okay.
But I can answer that question. It's a very long answer. Notice here I've got 6 solutions. We've added a new feature called Clean Stop. So I'm going to hit Clean Stop. What it's going to do is it's going to run through the last iteration that it's on, and then it's going to stop it. But I will not lose my solutions, which is nice. So let me run through and get a couple solutions here. Let it finish up solving the ones that it was working on. You'll see down here again, I'm using one core of my 2. And now it's finished. Notice it gives me an error saying the parametric analysis failed. It was user clean stopped, which means I still have my data. There's another feature that's nice to understand what solutions you have that are valid. So if I right-click on analysis and I go to Browse Solutions, I get a new window. Here it shows me what it is that's solved. And notice it shows me the parameters that were solved and whether they're valid or invalid, or if I wanted to, I can even delete the solutions. So this is very nice. If I have multiple different analyses defined under here, you would see all of them. So right now you see I have all these are valid solutions. So
Steve,
now,
if you change the schematic at all those are gone? In other words, if I just went into there and deleted R out, right? And now it says, I didn't want to do that, but what were my solutions anyhow?
I think it keeps them, Rich.
Yeah, where? And how do I find it? Like an ANSYS file, it's irrelevant. Once I build my circuit, I got my circuit. I can mess my circuit up, but I still have the TR0 files left, and I sort of can remember what I did. But here, once I've lost the schematic, I've lost my data.
I understand. Let me come back to that one at a later time, Rich, because I don't want to see everything I got. But I think there's a way to get that information. I have to. I don't know for sure the answer off the top of my tongue, though. So, okay.
Well, Steve, you can store the SDF file and read that in later if you want.
Okay, you can definitely do that too, Rich.
Store the what file? You can get back with me on that one,
Yeah, real quick, what Eldon said was if I go into my results folder and I just did IBIS transient, do I have to store every single SDF file though, Eldon?
There should be one right there. I thought you had it.
But each parametric has its own, doesn't it?
Well, every analysis set should.
So every analysis set has an SDF file?
And the SDF files you can load in directly, Rich.
Right.
And those are data solutions that I may have solved before. Okay, we can get offline afterwards on that one.
Okay. Yeah, they're equivalent. They're effectively a binary file, Rich.
And you all can read that.
Yes. Yes.
Yeah. You can open up that standalone.
Yeah. Well, that definitely will, and that would definitely be a workaround if we can't do it another way, which I think we might be able to, but that definitely will work. Okay. Sorry. Let me come through now. I'm going to right-click on results, and notice I've got I-diagram, and I've got a new block called statistical I-report. I'm going to create an I-diagram first. So I'm going to go to rectangular plot, and I need to understand what this net 8 is. I'm going to right-click here and create an I-diagram, rectangular plot. The UI was 10 nanoseconds, and it was net 8, okay? I'm going to hit New Report, and this is the traditional, well, helps if I select a variation. This is your traditional I-diagram that maintains all of the points. What I mean by it maintains all of the points is that I can come under here. Let me click here. Let me go to zoom range, and let me go to the color is going to be I'll go back to full range. I'm looking for sorry, I'm looking for a specific box. Eldon, did they move that box? They must have. The one that talks about the gradient versus solid.
Oh, the cloud plot?
Yeah.
You have to click the trace thing inside the project manager window, don't you?
Right, which is what I thought I did. I thought it was under I, and it should have been right here.
click there. All right, I hate to say it, but I think I've forgotten it.
Okay. Well, what I'm going to show you is when I say it saves all the transient data, I really need to get rid of that cloud plot bill. Is that I can scroll this data down here. Oh. I hit too many buttons too quick. I can come down here, give it 1 second to catch back up. I can come down here and I can zoom and take away iterations and just look at different bits. And the reason I can do this is I have all this transient data stored. The problem is if I do large number of simulations, millions to billions of bits, this is very problematic because, under attributes, there it is. Fine. Because there's so much data, you're talking gigabytes of data. And realistically, you cannot just take off a disk and plot that much information quickly. So that's your traditional transient eye. I'm going to go back to a cloud plot. Okay, I'm going to go back to turning off the zoom range, go back to full range. So this is what the transient eye. Remember I said we got a new type of plot called we got a new type of plot called statistical eye plot, but I must have hit a bad button because let me rerun it real quick. We have a new type of statistical eye plot, and the statistical eye plot will basically give me a picture. It's a JPEG picture of all of the information. But it does something else for me. It allows me to see the innermost eye diagram for all the different parametric variations that I ran. Not only does it let me see the innermost eye diagrams for all the parametric variations, it also lets me plot the minimum eye height and the minimum eye width for those variations. So what that means is I can look at the inner eye and get the interior eye width and the interior eye voltage. So I'm not doing a statistical solution. I'll just do a couple solutions here. I couldn't stop. Any questions on that?
In the definition, can you parameterize the UI interval?
Yes. Yes, you can.
Okay.
I've done that.
Okay, great. Go ahead, another question?
Well, I was just going to say, it seems like on 4.1 I've had problems when I try to do that sometimes.
You should not have any problems. I guess it depends on what you're trying to do with it, but I can't say that I've ever had any issues with that.
Well, there's some places you can't put that UI in. It's got to be global. Yeah, I know what you're talking about. You can parameterize it, but, you know, where do you parameterize UI?
Right. I think let's take that question offline because I get very specific.
Like in your report, you want to parameterize what that UI is and change the UI in there. You can't parameterize it right there.
Right. This is right. This UI means it's a statistical domain. It means it's not the time domain. This means something very specific. It doesn't mean unit interval from the perspective of parameterizing. It means unit interval from the perspective of, you know, we're now in a statistical type of domain, loosely speaking. I'm going to show available variations here. I'm going to select them, and I'm going to do new report. And now you're going to notice it's going to plot the variations that were available. Now notice, let me close this out. Okay. I'm going to dock this. I don't know if anybody knew you could do this, but you can dock this to the right. Notice, or you can dock to the left. Notice I have a statistical eye plot here, and I have all these different cases. And all of this data out here is what I call the cumulative mask function, the CMF data. So I can turn that off. So I'm going to turn that composite off. Now I have all these individual cases here. I also can do, and make this a little bit smaller here, where I'm just looking at the parameters, but let's say I don't want to just look at the parameters. I want to just look at this. Now I've got all these different cases, and I can highlight over them what they are. This is important because I have an eye filter that I can say min eye width, and it's going to find the one with the minimum eye width. Or it's going to find the one with the maximum eye width. Or I can do min eye height, and I can find the one with the maximum eye height at, this is talking at 1 unit interval, or the minimum eye height at 1 unit interval. So now I have all this information available to me specifically at the 1 unit interval and the zero crossing, or in this case it would be the 1.5 volt because it was a 3 volt system.
Was this now, your 100 by 100 space?
This is my 100 by 100. If I put it up to 500 by 500, that's very similar and very close to transient. So, but remember, if I do that, it'll take longer to plot, and it's going to use up more memory because that's very close to what transient is. But I can also add in eye measurements. I'm not going to do all of them. I'm going to do min eye width and add it in. I'm going to do min eye height and add it in. Notice now, for each one of these, I get a table out. Now, I'm going to come back and say none, but I want to come back to my legend and just show my variation key. So this is kind of ugly from this perspective. But there's a new feature that's very useful now. I can right-click and go down to Export Legend. See where it says Export Legend? I'm going to export this out, and I'm going to go to my documents for this case. I'm going to call this Steve Test. And it's going to create a CSV file. Inside that CSV file, I'm going to cheat, and I'm going to go back and open it up. Notice in this CSV file, I get a nice, easy-to-read CSV file. Now, granted, I have this very long path that shows me exactly what the variable sweeps were, but let me minimize this. It gives me the exact instance of what the sweep was here, and it gives me the eye width and the eye height values. So this is something that I can use for looking at large amounts of data very easily and very quickly and parsing it with a Perl script, if I want to use Perl, for instance. Any questions on that?
Have you invoked either Quick Eye or Verify yet?
No, not yet.
Okay.
Okay. I'm going to close this out. Okay. And that was it for my simple transient demonstration. Now, I need to go to IBIS AMI next. Before I go to IBIS AMI, is there anybody out there that's on this call that wants to understand what IBIS AMI is and how to use it? If there's nobody on this call that is interested in it, I don't want to waste time going through it.
Yes.
Yes, okay, so we have somebody. All right. So I'm going to add in another insert, next in circuit design, and I'm going to give this one, I'm going to hit none, and I'm going to call this IBIS_AMI. Okay. And I've got IBIS AMI here. Again, I'm going to come into here, I'm going to go to Tools, I'm going to import this array because I'm going to show you how to sweep the array. We'll do it quickly this time, though. I'll go to my training solution, and under DOE tables, I got Sweep Steve. I'm going to import that in. Notice it's bringing in all of these arrays. This was a question before. What does that do? Remember I told you it creates the array and the array index for me, and that's what it did here. So I'm going to hit Finish, and then it brings it in over here. Now I'm going to come back. Remember, I'm going to import my W element. So we've done all this once before. I'm going to go and add my files in. I'm just going to bring them all in. Hit OK. It's going to load them in and create a new component. I'm going to bring in my S parameter files. I'm going to do I'm going to do convolution again. Everything here is fine. I don't need it to create the arrays this time because I've already brought them in. I'm going to go to S parameters, bring those in, hit OK. It's going to load those in. Now I'm going to come and grab my components again. I've got custom 1 was created just now, and custom 1 for that was created. I'm going to come into here, wire it up. I'm going to go to my resistors, add in a couple of resistors. And I'm just doing this for demonstration purposes. These really don't need to be here, but it allows me to sweep something else. So I'm going to do R out here. I'm going to do RTX. RTX. I'm going to type in, remember, this is length. I'm going to call this so I can sweep it. I'll start at 10 inches, and then I'm going to enter a model name. And my model name I'm going to call, remember the name, if you recall, is 2-line, W underscore 2-line underscore array, open bracket, W underscore 2 underscore line is the index, close bracket. My S parameters, if we recall correctly, I'm going to add this one in. It was plus S4P underscore array, open bracket, S4P, close bracket, okay. Now, I'm going to start to differ a little bit. I'm going to add in a ground here, and a ground there. I'm going to go to a new component called, well, let me just show you where it's actually at. Independent sources. I have AMI source. So I'm going to grab my AMI source. I'm going to rotate it. And I've got AMI probe. If I go down to independent, or not independent, but just go down to probes, I've got AMI probe. I'm going to bring it over here. I'm going to rotate it. The plus goes with the plus, and the minus goes with the minus. Now, real quick, I think it's important for people to understand. IBIS AMI is essentially doing the same thing that QuickEye does. The difference between the two is that IBIS AMI, you have to get the .dll file and the parameters file from the silicon vendor. So in QuickEye, we have an ANSYS solution for FFE and DFE. And that's behavioral generic FFE algorithm, which is basically a delay filter with finite impulse response filtering. We also have a decision feedback equalizer that has basically a slicer that creates, ones and zeros, or ones and minus ones, depending on how you want to look at it. The idea behind IBIS AMI is that if you're doing SerDes designs, high-speed serial designs, you need to have the actual silicon solution. And the only way to get models, or for most people, the only way to get models for these kind of silicons are to get IBIS AMI models because they will contain a solution for the equalizers, whether it be a CTLE, whether it be an FFE, a DFE, adaptive CTLE. The silicon vendors are starting to provide IBIS AMI models that give you a solution to their actual equalizer technology. You can't see it because it's a DLL file. And then there's a parameters file that is what we call a .ami file that shows the parameters that you can sweep. Now, however, with all that being said, the way that AMI works is essentially the way that QuickEye works. If you look over here even, the AMI source file here, notice that from here to basically all the way to here, everything looks exactly the same as the QuickEye source. The only thing that's missing in our QuickEye source that this doesn't contain is we have a little block called FFE that we can do our FFE. But in replace of that FFE block, we have a library and parameters file for AMI because they're essentially the same theoretical solution using the same idea. So how do I use AMI? I'm going to point to an FFE file. I'm going to go to my library, and notice I can sweep the FFEs. Let me show you what I have in my in here. You see I have IBIS AMI, and the only thing that's important in here is I have this DLL file. So I can't read the DLL file, but that's what I can point to. So I'm going to point this to the DLL file. Notice this allows me to sweep different vendors' DLLs. So if I have a solution between two silicon vendors, I can sweep different silicon vendors now. So I'm going to point to IBIS AMI. I'm going to point to that .dll file and open and hit OK. I have this parameters file. Let me show you what the parameters file is. I've got 3 of them. I've created 3 of them. And in my params.ami, this is also provided by the silicon vendor. You'll notice that this one here talks about different methods that we can use. This is something that we created in ANSYS for generic solution. I'm going to use method 2. I don't want to get into what the differences between 1 and 2 are now at this point. Then in this case, I'm going to do FFE. I can enter any number of tap weights I want. I could also enter in 0.1 here if I wanted to. It doesn't matter. I can parameterize these things here inside a designer and have it get passed up into the designer interface if I want. Or, notice this is my params.ami. If I go back to here, I can create multiple files. And so if I come here and drop this onto here, you'll notice that my params1.ami has different values for my tap weights, excuse me. Notice it was 1 minus 0.1, 0.15, and minus 0.5. This one was 1 minus 0.2, 0.1, minus 0.05. I gave different numbers, and this was just created by me generically. So what I'm going to do here is I'm going to point to, if we go back and look at what was the name that was imported under projects, I'm going to come here and point to this. And you'll notice I have called it AMI params and AMI params array. So I'm going to click here. I'm going to type in the plus sign, AMI underscore params underscore array, open bracket, AMI underscore params, close bracket. Okay. Voltages, I'm going to go between minus 0.6 volts and 0.6 volts. Rise time, I don't know, let's do 50 picoseconds. Call time, 50 picoseconds. UI, let's do PCI Express Gen 1, 400 picoseconds. Notice now, I have duty cycle distortion, which was always there, transmit, random jitter, which was always there, but now I have periodic jitter. This is sinusoidal jitter that can get inputted at the source. This is also true for QuickEye. I also have uniform jitter, which is also imported at the source, which is also true for QuickEye. And
these are all high-frequency jitters that are amplified by the channel?
Yes. So these here are all inputted at the transmitter, and they will see the filtering characteristics of the interconnect, which means they'll undergo jitter amplification. So you have DCD, which is basically a bimodal solution. You have random jitter, which is Gaussian noise, or not noise, Gaussian jitter. Periodic jitter, which will be sinusoidal jitter, and then you can have a uniform jitter, which is a constant jitter.
How do you specify the frequency for the periodic jitter?
Good question. I want to take that one offline.
Okay.
Because I'm still working with development on that to get. I'm actually working with development to understand specifically how to invoke these in a way that I can let the users understand. Okay.
All right.
I just like in QuickEye, remember this AMI is very much like QuickEye. I also can control how long of an initial transient step response I want to run, and the default is 100. I also have bit patterns here. Remember, somebody asked a question earlier, and I told you I'd get back to you if I want to run 100,000 bits. Well, if I want to run 100,000 bits and I want just random numbers, I can enter the number in here, 100, 1, 2, 3,000 bits, and I'll just give it a random seed value. And that would be 100,000 random bits. If I want a more referred random bit pattern, I can do PRBS sources. For instance, this is a PRBS 7. And how many bits do I generate? 2 to the 7th minus 1, and the seed was a 0. I want to say, let's say I want to do a PRBS 23. Now, that is actually 2 gigabytes of data. That's a huge solution just in the data pattern itself. But I don't necessarily have to run all 2 to the 23 bits. I can run 2 to the 11th bits. So now I'm going to run a PRBS 23 data pattern, but I'm only going to run 2 to the 11th bits of that. And I can start it at bit 0, or I could start it at bit, I don't know, 2 raised to the, where's the raise button? 2 raised to the 10th. I could start it at the 2 raised to the 10th bit, but I'll just go ahead and start it at 0. So that's what I'm going to run. Okay.
Is that what seed means? Seed usually means to me is the seed for the polynomial.
Yeah, but not in this case.
So it's a misnomer in terms of the way. It's the start bit and the end bit is what you're talking about.
In this case, yes.
Is that true with QuickEye too?
Yes, because that seed there is the start bit. It is the polynomial is fixed in this case.
Right, but there's a seed for a polynomial.
Right, but the polynomial Right. So when you put a seed in for the polynomial, or wait, Eldon, am I saying that correctly?
Well, let's start over again, and maybe I can help.
Bring up the window and you'll see it. It's fairly obvious.
This seed value here, is that a seed to the letter X for the polynomial, or is that the bit that you start at?
I thought it was a seed into the linear generator for the PRBS sequence, but, you know, it could be like the tap weight, but, you know, I'm not sure, to be honest with you.
I thought it was the start bit because, how about that? We'll get back
But
to you on
yeah, why don't you get back?
Steve, you can put values that are not 0 and 1 in there.
Right, but the polynomial is fixed because it's a maximum length polynomial that's fixed. I know that.
Well, my guess is it would be a linear feedback shift register implementation, and that would identify the tap settings, but I'm not sure.
I don't think that's what Chin did, but we'll come back to an answer on that one, Rich, okay?
Okay.
So hit OK. Now, if I have a DFE, so this was a FFE or CTLE or whatever type of equalizer it was. If I have an equalizer at the receiver, I can also point to a library.dll file and the parameters file. In this case, I don't have a non-proprietary one that I can share. I have some, but they're all proprietary, so I can't show them. But you would point to it just like I did in this case, the same way. All right, so let's make sure I defined everything. And I did. Now, I'm going to come under Analysis, and I'm going to go to Add Solution Setup, AMI Analysis, and I'm going to hit 50 picosecond for the time step. Now, I want to show something in general. This is very important, and you will forget this. Oh, wrong button, because I always forget this. To date, I have not seen a 64-bit DLL for IBIS AMI. So, if you're running Designer on a 64-bit machine and you're running an IBIS AMI solution and it's got a 32-bit DLL in there, you're going to get an error. And you're going to be upset. And then you're going to forget what I'm going to show you, but call us up and I'll help you out. We have the ability to force it to use a 32-bit engine. So if you're running a 64-bit machine and you're trying to do IBIS AMI and the silicon vendors give you 32-bit DLLs for IBIS AMI, the way to run that is to use this checkbox that says use 32-bit engine. Okay? There's some things here I want to talk about those. Now, under AMI options, I don't want to talk about this. I can tell it not to create all the transit data because I'm only going to look at the statistical information. I don't need to create all of this. But I remember I told you I was going to show you the differences between a solution that does 500 by 500 binning versus a 100 by 200 in this case. So I'm going to hit OK. Now for AMI analysis, I'm going to do the default to start with. So I'm going to run this one. So this is the default This is the default analysis that's doing binning of 100 by 200. And as soon as it runs, so I didn't make any mistakes, I'll create a statistical iPlot. So I'm going to right-click, create statistical iPlot, and you only get 4 places to probe because of the IBIS AMI specifications. Initialize, after the source, after the channel, and then after the probe, which would be after DFE. In this case, I'm going to look after the channel. I'm going to hit New Report. And I get a statistical plot with an inner eye here. Again, notice it's kind of fuzzy. Now, let me go into here. And in AMI, I'm going to tell it to do the options that I set. Remember, the thing I changed in here was 500 by 500. And I'm going to right-click on this, and I'm going to reanalyze it. And it's going to use the options. So when it gets done running, you can, in real time, see how the eye is going to become more crisp and clear. And this is the difference of the binning information. So there's a trade-off of resolution versus speed of plotting. The more bits you run, the less of an effect it has on the binning information. If you run only a couple bits, you want high resolution. But if you're running millions of bits, the low resolution is fine because you're going to get lots and lots of plots on top of each other. And then you can see here, because I only ran a few bits, that I get a much more highly resolved eye. Any questions on that? That's a good example there.
Does it also truncate the first few cycles until it goes to steady state?
I did not truncate it in this case. You can truncate it, but I did not. If you look at the, and this is IBIS AMI, let me remember where to do that. If I go to options, under AMI options, it says iRecording start time. I had it set at 0.
All right, thanks.
Okay. Now, I'm going to delete this source because there's a lot of questions on QuickEye and Verify, and I'm going to come into here and show some new, we don't have a lot of time left, so I'm going to come into here and show some things about QuickEye and Verify. And I also want to do some, there's some new bit error rate plotting. It's changed, actually. I say it's changed. It's much improved, okay? I'm now going to go under Components. I'm going to go to Independent Sources, iSource Differential. I'm going to drop it down. I'm going to go to iProbes Differential. I'm going to rotate it. Okay. Remember, I can do multiple probes and multiple sources for crosstalk analysis. I'm just going to show a simple channel because I have it built right now. Notice that the output resistance is predefined, so I don't really need RTX, so I'm going to leave it there. I'm going to go between minus 0.6 and 0.6 volts again. Rise time, I do 50 picoseconds. Fall time, I do 50 picoseconds. I do 200 picosecond UI in this case. I got, remember, random jitter, periodic jitter, uniform jitter, and duty cycle distortion. Notice I've got step response UI. I'm not going to change that right now. Do encoding. If I change this to a 1, does 8-bit, 10-bit encoding on the input bits. I'll leave that on. Remember remember the difference between IBIS AMI and QuickEye is everything's the same except for I have an FFE data because I'm using the internal FFE here as opposed to the silicon vendors, and I don't have to point to any other files. And bit patterns, I'm going to go ahead and do a PRBS 23 again, but I'm not going to do that many bits. Let's do to the 15th minus 1. Okay. On the probe end, I have the name of it, so I'm going to call this V out. And then I have the source name, I point it to the source, and everything is set up. Now, I want to show you some new options that are available. By default, things have changed as well for QuickEye. So let me go up to here, and I'm going to add in a QuickEye. And when I say QuickEye, I really mean QuickEye and Verify in this case. Add solution setup, add QuickEye analysis. There's peak distortion analysis. It tells it which probe to use for the true channel. That will find the worst case bit pattern. Did everybody know that was available? Worst case bit pattern determination? Okay, I think that is a yes. I'm going to go to add solution setup, verify. This is the statistical analysis, and I'm going to hit OK. Now I'm going to go back to my options, add solution options. I'm going to go to I options. This is the QuickEye one. Notice again, I can do statistical eye plotting. The default is 100 by 200. The initial transient's 100, the maximum time to stop the transient step. So this says that, what if I make a mistake and I don't know what my through channel was? For instance, I refer a probe to the wrong source on accident. It's not going to, in version 4.1, it would just keep running and running and running and running. Now, after it hits 1 microsecond or whatever you default this to, it's going to quit. I also, in version 5, can tell it not to plot the transient results, so I won't keep all that data. I also, now this is a big change, I also have separate rising and falling step responses in version 5. In version 4.1, we would do the rising step response, take that, invert it, and you would assume a symmetric response for rising and falling. Now, in this case, it won't matter because I have an ideal driver. But if I'm doing something like an IBIS buffer model, it could matter. If I'm doing a silicon model, it could matter. But notice that the default is that the symmetric step responses are off by default. So this can, if you have this off, and if you don't turn this on, it can take a little longer to simulate compared to the first version because you have to do 2 step responses as opposed to 1 step response. But you'll get a more accurate solution. So it's kind of up to the user. Now, the other thing with this is that we have an auto extend step responses. We made the first attempt, and I haven't done a thorough amount of testing on this, but we made the first attempt at trying to automatically calculate out what the channel delay is, which means that instead of physically looking at the step responses to see that all of the ISIs died out, I can now tell it to auto extend it. I need to do some more thorough testing of this, though, so I'm going to hit OK. Any questions on what I've just defined there? Okay, I'm going to right-click now, and I'm going to analyze.
Do I need to instantiate the I source in order to do quick I or verify?
I'm sorry, what do you mean by instantiate?
Instantiate the I source. This is a new element to me. So instead of instantiate some voltage source, so I have to instantiate this I source. So ID is equal to 38.
Right, you have to put down the appropriate I source for Quick I and Verify solutions.
Okay, that's a requirement, right?
That is a requirement, yes.
Okay.
And the reason that there's an ID number here is because if I'm doing a solution that has multiple channels, so I'm doing an aggressor channel, victim channels, something with crosstalk in it, notice that the probe has to point to the correct source for the true channel to get the step response.
That's right.
And if I do
Yeah, but it's kind of a weird name. You don't get to choose the name.
Yes, you do. You click here and you select the source.
Yeah, but you can't change the name of that source.
No, that's why because it's ID though. That's why the ID number is shown on the schematic. It's based off the ID equals 38. So if I look here, you'll see it's AI source, but the ID number is 38. That's why it's done that way. Similarly, if I'm doing an FFE, I have to tell it what the compute reference probe is. So for instance, if I would tell it to do one tap down here, I would have to tell it what the reference probe is. It's called probe 39. The ID number is 39. That's why it's shown on the schematic.
You only need that for adaptive equalization.
You only need that if you're going to do FFE here.
FFE, and then DFE, they go in the other way.
And DFE,
no, FFE without. If you're figuring the taps, if I put the taps in, you don't care about that, right?
That's correct. Because if you're putting the taps in, I don't have to do a tap weight calculation.
Right, exactly.
Correct. Okay, right now it's running the verify solution, I believe, and it's doing an 8B, 10B calculation if I am paying attention here. It is possible that I ran so many bits that it's still calculating the quick eye response.
How many bits did you run? You didn't go to 2 to the 23rd, did you?
2 to the 15th or something. That's quite a few. Let me abort this just to make it quicker.
You put in a different source than IBIS AMI. Can you use IBIS AMI with Verify?
No. IBIS AMI is a very specific standard, and they don't support statistical type of solutions like Verify does. If you notice in IBIS AMI, with IBIS AMI, you can't. With IBIS AMI, you're not able to probe anywhere you want in the channel either. IBIS AMI specification gives a very specific location of where you can probe. You can probe at the bits that are coming out. You can probe after the equalizer model on the transmitter. You can probe at the end of the channel or end of the interconnect, and you can probe after the receiver equalizer. But you cannot probe anywhere else. You can't probe in the middle of the channel.
What about with Quick Eye? Can you use IBIS AMI with Quick Eye?
IBIS AMI is no. Again, remember I said IBIS AMI is a very specific standard IBIS AMI and QuickEye are doing the same thing, though. It's just that in IBIS AMI, you have silicon vendors' equalizer models as opposed to doing the QuickEye equalizer models.
Yeah, okay. Yeah. I have to drop off for my next call. Thanks for the...
Okay. Thank you. I wanted to show some bathtub curves if this ends up showing, because there's a new feature with showing bit error rate eyes that I think is important. But if you need to drop, I understand it. I'm just waiting on the solution. The solution shouldn't be too much longer. Any other questions out there? I know what's taking so long. It's what I thought it was. I'm going to turn off the AP10B encoding. All right. I'm going to just run verify and analyze. With respect to bathtub plots and bit error rate contour eyes, we now have the ability to put a bathtub plot down and put the markers independent anywhere you want on the bathtub curve plot. With respect to bit error rate eyes, you can now select a very specific bit error rate and look at the eye diagram. Along with, you can export out tables of that information as well. So I've solved this now. I'm going to come to results. I'm going to create a standard rectangular plot. I'm going to go to verify. And notice it's a bathtub curve. I hit new report. Well, I don't have obviously I don't have a solution there, so because my bit error rate's terrible. Let me go back into here, families. Let me see if I select a different voltage. I probably need to equalize this, I guess, because I need to equalize this channel because I don't have a solution space. So let me come to feed forward equalization. Let me put in 4 taps. Start location is -1. Let me put probe 39, okay. And let me analyze it. Now I have an equalizer on there. It should open up the eye.
Is there any jitter separation as a post-processing?
Not yet. I have a hard time. I have to admit, this is an open question to everybody. I have a hard time understanding jitter separation in a simulator, specifically in a simulator, because I am adding in the jitter, and because I add it in, why do I want to re-separate it out?
Well, you can do the jitter profile on the eye diagram.
You can do that as well. And I guess the only argument that I can think of is that one may argue that, well, Steve, what happens if I add in transmit jitter and it gets amplified and I want to separate it out at the receiver? I guess that is a usage case I could argue for, but that's a discussion as to why do you...
The problem is that specifications break down jitter to all these different funky buckets that are like pulse jitter and total jitter and and edge jitter and all of that, and it's terribly confusing when you have a simulator to be able to go between what a specification specifies in jitter and what you report as jitter.
Okay. Real quick, back to here. I'm going to go 1E minus 12. I'm doing a contour eye, and I'm going to put in 1E minus 4. And if I count on my fingers, so 1E minus 4, 5, 6, 7, 8, 9, 10, 11, 12, that's 9 contours. if I want a nice equally spaced distance. So I'm going to put 9 in here, and now I can look at my different contours. You'll notice I don't have a 1e minus 12 solution. I only have a 1e minus 4 and a 1e minus 5 solution. I can also say I just want to look at one. I can go say 1e minus 4 and 1e minus 4. Now you see that I have a 1e minus 4 contour eye that I can measure the characteristics on. Similarly, for the bathtub curve, create standard report, rectangular plot, new report. Oh, sorry, I got to select the right analysis. New report. I get a bathtub curve now, and as you expect, it was not a very clean solution. I need to go to scaling. Okay, guess it is log. Because I don't have anything past 1e minus 2, 3, 1e minus 4 is the best solution that I have. But the one thing that's changed now is I can do markers, delta marker, and I can put this anywhere that I want on my graph now. And, well, I say that now, I'm not able to do it. We're adding it in so you can probe anywhere and do delta markers anywhere on the plot itself. So I'm going to go ahead and conclude. There's another. I've showed you one way of doing text arrays, which was this import feature. You don't have to do it as an import. You can go to design properties and go to tuning. Or you don't even have to go to tuning. Go to local variables, and you can add an array yourself manually. So I can call this Steve array. I can add in rows, and I can type in quotations marks, for instance, at $ project dir slash s underscore params slash 1 underscore inch dot s4p. I can go in manually and create these arrays if I want. Let me delete. Let me copy this. And I know I also have a 20-inch in here. And let me delete this. Delete, delete, delete. Okay, I'm going to say okay. Then here I can go into, now I have the array created, I need to add an array variable index. So I go to here and I point to Steve, and I'm going to call this Steve underscore II. And I have it start at 0, and I hit OK. Now I've got Steve and Steve II. I hit OK. I can come into here now, here, and add this in and call this Steve underscore, I think it was array, and then Steve underscore II. Nope, it wasn't array. It was Steve. I can come into here now and go +sign Steve bracket Steve underscore II close bracket OK. Now I can create my own optometrics. I don't have to input it from a file. I can come into here and go to add Steve II, and I can do single values, or I could do linear step. I could start at 0, and I have two things in there. I can go to 1, step size of 1, and hit add, and hit OK. And now on my table, I'm sweeping Steve from 0 to 1. So I can create up all my parameters manually and do a Monte Carlo that takes into consideration every single case. So basically creating up truth tables here of things to sweep, as opposed to importing an array from a file. So with that, I'm going to go ahead and end today's training session. Is there any last questions?
Is there any documentation or help notes or tutorials regarding Verify or QuickEye on your web?
There is documentation that specifically talks about QuickEye and Verify in the help menus. I guess the question is, there's also several presentations on the web page about usages and There's a couple design papers on QuickEye and Verify as well. It depends, I guess, to a certain extent as to what it is you're looking for.
I'm going to need to QuickEye and Verify and try to see what usages it can be useful. So
it's useful. It's useful for any type of high-speed serial design that you have very minimal usage of non-linear components. It's also useful for single-ended designs that you have very little usage of non-linear devices. The normal usage case is high-speed serial designs. However, if you're doing memory applications and you're using an IBIS buffer for memory applications, you can also use it. There's some tricks and some things to understand to make sure you're getting accurate results, but you can use it for pretty much anything you want unless there's a large dependency on nonlinearity.